Hey everybody, Mr. Lake here with another chemistry video. We're getting back into it. Today we're going to talk about something called the octet rule. Now, in order to understand this, you'll need to remember valence electrons and a little bit about valence electrons. Really, you just need to remember valence electrons. So, just a quick recap. Remember that electrons fit into these spaces around the nucleus of an atom, and those spaces are called orbitals. Now, the outermost set of orbitals that an atom has, that's called its valence shell. Those are the electrons that exist kind of like on the outermost parts of the atom. Any electrons that exist on orbitals underneath that or inside of that, those are called the inner shell. The valence shell is really, really important because it is what interacts with the outside world. The inner shell electrons don't really interact much with other atoms or, the atom's surroundings or anything like that. But the valence shell does. It's very important for that reason. You can kind of think of it as like the valence shell is like the skin of the atom. Maybe that's a disturbing image. I'm not sure. But like think of yourself, right? What organ interacts with the outside environment? It's your skin, right? That's how you sense the outside environment. That's what interacts with the outside environment. Like that is the outermost layer of you. Your internal organs are important, but they don't really interact with the outside. In the atom, it's the same way. The inner shell electrons are important, but they don't interact with the outside. It's only the valence shell, the ones on the outermost um, reaches, that do. Now, something that you might remember also about valence shells or valence electrons is that an atom can have eight of them. Eight. That's eight. An atom can have eight valence electrons maximum. It cannot have more than that. And we talked about um, kind of how to identify when you're looking at the periodic table how many valence electrons something will have based on what column it's in. Well, let's take it a step further. Not only can every atom only have eight electrons, but every atom wants eight electrons. Every atom, if it has a chance, will do what it can in order to have eight electrons in its outermost valence shell. But if you look at the periodic table, only one group of the periodic table has eight valence electrons without trying. And those are the noble gases, right? You may remember that I mentioned that noble gases are really not reactive at all. They are very unreactive. And that's because they already have eight valence electrons. So they're not really going to try and do anything in order to get or lose any electrons. They've got what they want. Everybody else on the periodic table, though, doesn't just have eight valence electrons, but they want it. And so they're going to try and they're going to do what they can in order to gain or lose electrons to get it so that their outermost valence shell has eight valence electrons. They want a full valence shell. And this is really what leads to most bonding and chemical reactions is just atoms trying to fill their octet. The reason that atoms naturally want to fill their octet, I keep saying want, atoms don't have brains. Atoms, as far as we know, atoms don't have a consciousness where they are like, oh, yeah, I want eight valence electrons like a human might want to collect all 150 Pokemon. And I know there are more than that, but OG 150 is all that I subscribe to personally. Atoms don't have personalities or desires, but as all things in the universe tend to do, atoms like to be as stable as they can be. And it turns out that having an octet, a full valence shell of electrons, is the most stable that an atom can be. And so they want to be as stable as possible. Now, let's think about what it would take for an atom to have a full valence shell, eight, and a full octet of eight valence electrons. Something that is on the periodic table that has a lot of electrons already, like maybe one of the halogens that has seven valence electrons. Obviously, to fill the octet, to fill their valence shell, they're going to want to just gain an electron. They've got seven. They just need one more. So they're going to want to try and gain that electron in order to fulfill the octet. But think about an atom that only has one or two electrons in its outermost valence shell. Well, something with one electron in its valence shell, it could gain seven electrons. But that's a lot of collecting. That's a lot of work or interaction, or it's a lot for an atom to try and get seven electrons from somewhere. However, since it only has one valence electron, what if it lost that electron? If it did that, remember that all of the shells beneath whatever the outermost shell is, they're all full. So if something only has one valence electron, it's going to try to lose that electron, because when you lose the one electron in your valence shell, that whole shell just kind of doesn't exist anymore. And now the level below it is the outermost shell of electrons, and it's already full. So sometimes losing electrons is the best way for atoms to achieve the octet rule, which is kind of counterintuitive. Let's go through some examples. Let's talk about, what would happen in different situations depending on where an atom is in the periodic table. Let's start with lithium. It would be really helpful if you had a periodic table out in front of you, or maybe just pause this video for a second and open up ptable.com in a separate tab so that you can look at a periodic table as I'm working through this and as you're working through this. Let's do a kind of midnight blue today. Lithium is in the first column of the periodic table. Now, we already know, based on, how we identify valence electrons in the periodic table, we know that lithium has one valence electron. So if we were going to draw an uh, electron dot diagram of lithium, it would have one dot, right? Now, lithium wants to achieve the octet rule, as do all atoms, but it only has one valence electron and it wants to have eight. So what it could do is it could gain seven, or it could lose the one that it has. And in all cases, atoms are going to do whatever is easiest, whatever requires the least number of gaining or losing electrons. So in this case, it's going to lose the one. Now, here's where it gets a little interesting. That means that it's going to form an ion. Remember, an ion is an atom with a charge. This is how atoms get charges. If you were ever wondering, we were talking about, isotopes and atoms before with charges, you're like, wait a second, why would an atom have an unequal number of protons and electrons? It's for this reason. So lithium has a certain number of protons, and it has generally will have a certain number of electrons that equals that number of protons and will give it a neutral charge. But if it loses this if it loses this electron, it's now going to form a positive one ion, because losing one electron means that you're losing a negative charge. And so the protons are going to outnumber the electrons by one, and you're going to have a positive one charge. So this is how ions are formed. Lithium, therefore, is most likely to form a plus one ion. We're learning lots of stuff at the same time. And if you want to draw an electron dot diagram, generally you would just draw that. No valence electrons, because it lost its valence electrons. Although technically, maybe it has a full shell of electrons, but let's stick with let's stick with this for now. It has lost its valence electron, right? Okay, next example. Beryllium. Beryllium is in the next column of the periodic table, column 2, or group 2, or family 2. That means that it has two valence electrons. Its electron dot diagram in this standard neutral form is going to look like that. Now, to fulfill the octet rule, is beryllium going to gain 6 electrons and bring it up to 8? Or would it be easier for it to lose 2 electrons? It's still easier to lose electrons in this case, so it's going to lose 2. Well, what happens if something loses 2 electrons and loses 2 negative charges? It's going to form a 2 plus ion. So everything in the second column of the periodic table, including beryllium, is most likely to form a 2 plus ionic charge, which would make its electron dot diagram this, because it just lost those 2 electrons. Now, if you're looking at the periodic table, we're going to skip over the whole transition metal section, that whole D block in the middle. We're going to skip to column 13, which has boron at the top. Boron has 3 valence electrons, which is going to make it likely to lose 3 because it's going to be still easier to lose 3 than gain 5. So everything in this column, including boron, is going to form a 3 plus charge. Pause the video and take a few seconds or a couple of minutes, however long it takes you, to fill out the rest of this table. I will stop talking for a moment. I'll wait, pause the video, finish this, and then I'll show you how the rest of it is done. I'm back. Let's go over the rest of this table. Carbon. This is where it gets interesting. I kind of left you hanging right at the point where things were going to shift around a little bit. So let's go through this. Carbon has 4 valence electrons. Boop, 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 boop. That's its electron dot diagram. Uh, okay. It could lose 4 or it could gain 4. Which one of those is going to be easier? Well, neither. They're the same difficulty. And so it is everything in this column with carbon. These are kind of the interesting ones. You might notice that that column lines up with quite a few of the metalloids as well. They're going to gain or lose 4 valence electrons, just kind of depending on what's easiest. So if they're around a bunch of other atoms that all want to gain electrons, they can give their electrons away. If they're around a bunch of other atoms that want to lose electrons, then they could take those extra electrons and fill their octet with it. They are very lucky in that way. They're very versatile. One of the reasons why life on Earth is carbon based is because of how versatile that element is. But I'm digressing. So, how should I do this? Carbon, therefore, could form a 4 plus or a 4 minus charge, which means that it could either lose all of its valence electrons or gain electrons all the way until it has a full octet, like that. Now things are actually going to get a little bit easier from here on out, and I'm going to disappear, and you're just going to hear my voice. Don't be creeped out, but just so that we can see the rest of this table, I'm going to go through this, and I'm going to go through it kind of quickly. Nitrogen and everything in the column with nitrogen has 5 valence electrons. That means that it's going to have 5 dots. Sorry, a little sloppy here. In its electron dot diagram. And now we're in the realm of things that are going to gain electrons because it's going to be easier for nitrogen to gain 3 electrons than lose all of the 5 electrons in its valence shell. So nitrogen's going to gain 3, which means what happens to the charge of something when it gains 3 electrons and an electron is negatively charged? Well, it's going to form a 3 minus charge. And that will complete its octet. Oxygen and everything in the column with oxygen has 6 valence electrons. It's going to be easier for it to gain 2 than to lose 6. And so oxygen and everything in this column is going to form a -2 charge, giving it the full valence shell. Fluorine And everything in the column with fluorine has 7 valence electrons. Obviously, it's easier for it to gain just 1. We talked about this example, than for it to lose 7 electrons. That would be crazy. And so everything in the halogens, which is the second to last group on the periodic table, will likely form a -1 ion. And remember that when charges are just single charges, we usually don't write a number there. And that's going to fulfill the octet rule for everything in that position. And now we get to everybody's favorite. Actually, I don't know if they're anybody's favorite, but everyone's favorite, the noble gases, including neon, which already have 8 valence electrons. Well, if something already has an octet, what's it going to gain or lose? Nothing. Not applicable. What ion is formed? Not applicable. What's the electron dot diagram? I mean, we just don't have to draw anything there because it would be the same as what we've drawn before because it's not going to gain or lose anything. So hopefully that made sense. That's a little bit about valence electrons. Now, what we're going to talk about in the next video is how you can use your periodic table. I mean, you already can kind of, I've been saying it all through this entire example, but you can hopefully already see the pattern on the periodic table. But in the next video, we'll go over what the pattern is on the periodic table and how you can use that to determine what kind of, not just how many valence electrons and what charge different atoms are going to have based on where they are in the periodic table, but also we're going to get into knowing what kind of bonding might happen between atoms on the periodic table. I'll leave that for later. Until next time, take care, everybody. I will see you in the next video.